Please welcome Acronym's CMO and Managing Director, Mike Grehan.
Hey guys, good morning. I'm glad somebody from the back of the room did that, because if you were hanging around yesterday, you'll know that most of my job is actually introducing the speakers. And I was trying to figure out, how do you introduce yourself? How are you going to go out and do that? Anyway, glad that you were able to join. Today's a kind of a special day. I don't know whether it's just me, but I've been living in the US for a long time, and today is International Women's Day. And it seems to be celebrated more around the world than it is here in the US. So I just thought I'd give that some acknowledgement. Certainly my wife, who is from Russia, it's a huge day. So acknowledging the contribution that women make to the planet in everything from creativity, technology, science, economy, the whole thing. Today's a great day to celebrate that. My mother is actually very old and terminally ill, so this will be her last International Women's Day. But it's a great opportunity to thank her and all women for the greatest gift, and that was the one of birth and bringing me safely into life. So celebrate today, ladies. It's your day today. All right. So I've been in this industry for a very long time. I actually came online back in 1995 and started doing search full-time a little while after that. Google wasn't around at the time, so there was a whole bunch of search engines before Google, believe it or not, about 100 maybe. The big one was a search engine called Alta Vista. And I kind of figured out early on how I could do stuff at Alta Vista to make documents rank higher. And I remember one day one of my clients came to me and he was asking about how we were doing. I said, we're doing really well. You're actually the top 30 at Alta Vista. He said, I'm in the top 30. I said, no, you are the top 30. All 30 pages, they're all. I was spamming like you wouldn't, but I just thought I was doing a great job for my client, you know. There was kind of this wanted poster that was hanging for me out in Alta Vista at the time. But it was a guy from Alta Vista, after I'd written the first book on SEO 20 years ago, dropped me a note and said, there's another book that you need to read because you kind of got it, but you don't really fully understand this thing. So the book was called Modern Information Retrieval, written by a guy called Gerard Salton. And he is the father of information retrieval science. And it just blew me away. It was a very hard thing to read. But when I got to understand what he was explaining, I understood so much more about what was happening in search. And eventually when Google came around, exactly what was happening there. But the interesting thing is, I didn't realize when I started on that journey, I was actually learning so much about artificial intelligence, because information retrieval is in fact a subset of artificial intelligence. And that's what this session is about. I'm a member of ACM, have been for a very long time. So I get to see a lot of what's going on in the research field. And certainly here at this conference, and within the industry, there's a lot of talk about artificial intelligence, what it is, what it can do. What I've decided to do today, instead of me just standing up and talking around a bunch of slides or telling what I know, is I've selected some videos. So grab some popcorn. This is the way it's going to go. I want to show you a short series of videos from the people who are involved in creating the technology, making the technology, showing you a little bit more behind the curtain how it works, and then have some thought about how it really is going to change what it is that we do in our working lives today. So the notion of artificial intelligence, everybody has their own idea. What I've chosen to do today, I thought, wouldn't it be great if we could actually have an engineer from Google, somebody who actually does this stuff, give us an explanation on what they believe artificial intelligence, in particular what machine learning is all about. So let's start there.
The world is filled with data, a lot of data. Pictures, music, words, spreadsheets, videos, and it doesn't look like it's going to slow down anytime soon. Machine learning brings the promise of deriving meaning from all of that data. The value of machine learning is only just beginning to show itself. There's a lot of data in the world today, generated not only by people, but also by computers, phones, and other devices. This will only continue to grow in the years to come. Traditionally, humans have analyzed data and adapted systems to the changes in data patterns. However, as the volume of data surpasses the ability for humans to make sense of it and manually write those rules, we will turn increasingly to automated systems that can learn from the data, and importantly, the changes in data, to adapt to a shifting landscape. We see machine learning all around us in the products we use today. However, it isn't always apparent that machine learning is behind it all. While things like tagging objects and people inside of photos are clearly machine learning at play, it may not be immediately apparent that recommending the next video to watch is also powered by machine learning. Of course, perhaps the biggest example of all is Google Search. Every time you use Google Search, you're using a system that has many machine learning systems at its core, from understanding the text of your query to adjusting the results based on your personal interests, such as knowing which results to show you first when searching for Java, depending on whether you're a coffee expert or a developer. It wasn't that long ago that when a company or product had machine learning in its offerings, it was considered novel. Now, every company is pivoting to use machine learning in their products in some way. It's rapidly becoming, well, an expected feature. Just as we expect companies to have a website that works on your mobile device or perhaps an app, the day will soon come when it will be expected that our technology will be personalized, insightful, and self-correcting. As we use machine learning to make human tasks better, faster, and easier than before, we can also look further into the future when machine learning can help us do tasks that we never could have achieved on our own. Thankfully, it's not hard to take advantage of machine learning today. The tooling has gotten quite good. All you need is data, developers, and a willingness to take the plunge. For our purposes, I have shortened the definition of machine learning down to just 5 words. Using data to answer questions. While I wouldn't use such a short answer for an essay prompt on an exam, it serves a useful purpose for us here. In particular, we can split the definition into 2 parts: using data and answer questions. These 2 pieces broadly outline the 2 sides of machine learning, both of them equally important. Using data is what we refer to as training, while answering questions is referred to as making predictions or inference. Now, let's drill into those 2 sides briefly for a little bit. Training refers to using our data to inform the creation and fine-tuning of a predictive model. This predictive model can then be used to serve up predictions on previously unseen data and answer those questions. As more data is gathered, the model can be improved over time and new predictive models deployed. As you may have noticed, the key component of this entire process is data. Everything hinges on data. Data is the key to unlocking machine learning, just as much as machine learning is the key to unlocking that hidden insight in data.
So that's a really good way of describing exactly the way they think about it at Google. A lot of what we're going to be learning as we move forward with technology is all about the interaction between man and machine and the way that we get to understand each other. This great guy here actually is one of a series of the earliest hypertext thinkers. I actually tracked hypertext back to 1945, some time ago. He's the inventor of the computer mouse, which was the first way of interacting with a machine, man and machine interacting together. I guess he never knew when he invented the mouse that it would be associated with these words: "You piece of crap, just work. Why don't you just work?" Don't tell me you haven't done that with your mouse before. But he talks about augmenting human intellect. I guess digital assistants, this is what this subject is all about, but that sentence just below there about performing tasks and offering services with capabilities beyond the ordinary powers and reach of human beings. So there was something that guy just mentioned there before about the data is becoming so great that humans can't scale it and machines will begin to do it. There are 2 areas with AI. There's strong AI and weak AI. Weak AI is actually really cool. Strong AI is the one where people think we're at now, where machines can think. They can't actually think. They don't really understand meaning. You can ask Google questions and you get responses that are actually factoids, but if you ask a question about morality, you probably hear Google saying, "Ask me one about Justin Bieber," or something, you know? The weak AI, the best way that I've come across trying to explain the difference with weak AI, which is really smart, is just to look at the digital assistants and the way that we interact with machines. So an autonomous vehicle, for instance, if you get into it and say, "Drive me home," fine, it will drive you home. And if you go to Siri and say, "Order me a pizza," Siri can order you a pizza. But if you ask the autonomous vehicle to order you a pizza, nah. And ask, "Siri, drive me home," no, that ain't going to work either, you know? Google has a way of talking about this. They call it artificial intelligence, which I think is kind cute. So we talk a lot about question answering. I've just covered some of that there. Strangely enough, Watson is more famous for answering questions and cracking the code there, particularly with Jeopardy. In fact, what Watson did was entirely different. Watson took the answer and then took the answer, and then came up with the question, and then came up with the answer, whichever way around it was. It really is difficult to do, but this is a fascinating look at what happens under the hood with Watson, 4 not so easy steps on how machines are answering questions.
How Watson answers a question in 4 not so simple steps. The first person mentioned by name in The Man in the Iron Mask is this hero of a previous book by the same author. This is a typical Jeopardy clue, presented in the tricky Jeopardy format that can be pretty difficult for a person to understand, much less a computer. Remember, a computer understands code, ones and zeros, not nouns and verbs or people and places, let alone the relationships between them. Watson can't see or hear, so audio and visual questions are off limits, but everything else is fair game. And of course, it's impossible to know everything. As Alex Trebek often quips, the hardest Jeopardy question is the one you don't know. How does a computing system reach a single answer to clues posed in human language? Unlike traditional databases designed for computers, real language is implicit, ambiguous, and full of complexity. That's one of the reasons why, until now, computer searches have only spit out documents filled with keywords. It's been up to us to find the answers in those documents. Like our brains, Watson's knowledge base is entirely self-contained. Except while our brains fit in a shoebox, Watson's brain takes up more space than 8 large refrigerators. When Watson answers a Jeopardy question, there is no internet or helpline, so Watson consumes a steady diet of information to prepare for a game. Watson needs to absorb so much information because Jeopardy is open domain, which means it can ask a question about anything. So Watson reads, analyzes, and tries to understand millions of books and documents, content written in the way humans communicate, before it gets anywhere near a game board. Never before in the history of computing has a machine been able to so precisely answer such a wide breadth of questions in such a short time. Let's see how Watson does it. Step 1. Question analysis. The first thing Watson does is parse the question into its parts of speech and identify the different roles the words and phrases in the sentence are playing. This helps Watson determine 2 distinct things: what type of question is being asked and what the question is asking for. During this early stage of the process, Watson doesn't know how to find the best answer yet, so it increases its chances by looking at many different options of what the question might be asking for. Step 2. Hypothesis generation. For each interpretation of the question, Watson quickly searches through hundreds of millions of documents to come up with thousands of possible answers. At this point, quantity trumps accuracy. It's more important for Watson to generate a large number of possible answers and narrow them down from there, because if the correct answer isn't included during the initial sweep, there is no possible way for Watson to identify and justify the right answer at the end. Step 3. Hypothesis and evidence scoring. Of course, it's not enough for Watson to just come up with answers. It has to support and defend them. So after downgrading obviously wrong answers, Watson finds passages from many different sources to collect positive and negative evidence for all of the remaining possibilities. Watson understands these passages having learned the relationships between words. Relationships such as books have heroes, or authors create characters. Scoring algorithms then rate the quality of this evidence based on everything from the source material's reliability to whether the time and location appear correct. There are still hundreds of possible answers left, so thousands of algorithms work in parallel to score the evidence for each and every one of them. Remember, this must happen in seconds. Step 4. Final merging and ranking. Different types of evidence are better at solving different types of questions. So just like a person learns from practice, Watson uses the experience it gains from trying to answer similar questions in order to weigh the importance of its different types of evidence. It's not about memorizing trivia. By playing thousands of practice games, Watson learns how to weigh, apply, and combine its own algorithms to help decide the degree to which each piece of evidence is useful or not. These weighted evidence scores are merged together to decide the final rankings for all of the possible answers, with the highest ranked answers appearing in order on Watson's answer panel. In Jeopardy, contestants lose money if they buzz in with the wrong answer, so Watson estimates its confidence as to whether or not its top answer, along with every other answer possibility, is correct. This confidence is based on how high the answers rated during evidence scoring and ranking. If Watson's confidence for its top answer is low, under 50% for example, then Watson won't answer. This is an important step for computing. Watson knows what it knows, and it knows what it doesn't know. There is no fixed confidence level deciding whether or not Watson buzzes in. The threshold is constantly changing based on how well Watson is doing relative to the other players and how much money is left on the board. In this case, Watson arrived at its answer with a 78% confidence. For that stage of the game, it was a high enough confidence level to buzz in, and it won Watson $800 in the process.
Who is D'Artagnan?
IBM is using Jeopardy as a way to push the science of deep analytics and natural language processing forward.
So that gives you a kind of indication of the machine learning to do stuff itself. One of the important things in there, or two of them, Watson knows what it knows, but more importantly knows what it doesn't know, and Watson develops the algorithms itself in order to be able to weigh the scores. So we talk a lot about questions and answering, certainly when it comes to Google. Speech recognition is really important, and trying to move away from keywords and understand natural language is where everything is going, certainly at Google. So there is a guy at Google who heads up their team there for conversational search is what they call it. He's been there for about 10 years. He's actually based in Switzerland. So he did this presentation about 18 months ago. There's a reason that I'm telling you it was 18 months ago. But it was absolutely fascinating because now we take this understanding that the machine has and put context behind it. What does that mean? Well, watch this little demonstration. It's very close to my heart because they start with the subject matter, which is very close to Acronym, the building that we're based in.
Where is the Empire State Building?
Empire State Building is at 355th Avenue, New York, United States.
I want to see pictures.
All right, pictures for Empire State Building.
How tall is it?
381 meters, 443 meters to tip.
Who built it?
The Empire State Building was designed by William F. Lamb, Yasuo Matsui, and other architects.
When?
Construction for the Empire State Building started in March 17, 1930.
So you notice that I only said one time Empire State Building, and I even a very short, very ambiguous query like when. We can realize that when actually means when was the Empire State Building built. This is all trying to interpret things based on the context. Let's continue. Show me Italian restaurants around there.
Italian restaurants, here you go.
How about French?
All right, French restaurants.
Call the first one.
Calling I Fiori.
So that's really cool, the way that you can understand that now the machine has the context and keeps that context as you go through that one short question of just when is really important. He actually went on to call one of those restaurants, by the way, if the video carries on. He was in Europe, it was like 3 o'clock in the morning. I don't think they appreciated the call. I mentioned that keywords themselves are not as important as that. Don't worry, they're not going away anytime soon, but they don't tell you a lot. It's just a quick way to get to some content that you then have to process yourself. I wanted to have a look in terms of understanding intent and behind a query, the kind of things that Google could now interpret. I'm not quite sure where I got this one from, but take a look at what the query actually is. I can't remember it. I can't actually see. Oh, I just dropped my mic. It's something about a scientific spinning wheel underground in Switzerland, yeah? You see that? But look at the answer. The answer is all about, thank you, big underground scientific wheel in Switzerland. What the heck does that even mean, you know? But look at the answer. The answer is all about Large Hadron Collider. So you can see that many of the queries that are used now, when you go to the content, the words that were used in order to surface that content don't actually even appear in the query anymore. The reason that I mentioned about the guy who's head of conversational search, it was 18 months ago when he did that demonstration that you've just seen, okay? A couple of months ago, he did another one that just blew me away. And I'm just using this in text to give you an indication of how it translates now when it goes to speech.
But the range of questions that people are asking is really big. So for example, one type of more long tail rare questions could be something like, what is the name of the movie where Tom Cruise acts in it and he plays pool, and while playing pool, he dances?
Here is some information about The Color of Money. Former pool hustler Felsen decides he wants to return to the game by taking a pupil.
So now let me show you what type of experiences you can have if you connect these types of voice interactions with other types of services which we could have. For example, translate. Be my Vietnamese translator.
Understood. I will translate all your following messages to Vietnamese. To stop, just say, stop translation.
Hey, I have a problem. Can you help me?
Hey, tôi có một vấn đề, bạn có thể giúp tôi.
I lost my luggage in the train.
Y bị mất hành lý của tôi trong chuyến tàu.
Stop translation.
So the most interesting thing there, apart from the fact how cool was that, figuring out the color of money with that query, is the fact that he's now moving progressively from one app to another, that he doesn't have to log out of one, log into another one. And this is what you're going to see in the future. So keywords, as I say, this is the smallest element of the English language. We've been used to in search using keywords as that way to connect with content. Over at Google, they do a lot of, they're probably the biggest and fastest movement when it comes to the whole realm of artificial intelligence. But an area called artificial neural networks is where they excel in. And these deep neural networks are so advanced you wouldn't believe. But I've actually got an engineer here, this is very cool, who, where there are no keywords involved, will show you just how advanced the technology is with a simple example of what's the difference between a cat and a dog.
One of the things that I think really makes it unique in terms of machine learning frameworks is that you can actually build a model in, let's say, 5 or 10 lines of code, and then take that model and scale it all the way up to production. So you can train that model on a cluster of tens or even hundreds of machines, and then take that model and serve it doing super low latency predictions. So let's have a little discussion about what it is that I mean when I say model specifically, and how machine learning relates to that. Here's a simple problem. Predict whether an image contains a cat or a dog. This is something that would be difficult or even impossible to do with traditional programming, because how do you make a set of rules that define what is a cat versus a dog? And then on top of that, how do you capture all of the variations like breeds, poses, and then the brightness and the scaling of the image, all of that sort of thing. So what we can do instead is make a neural network, which is like an extremely simplified version of how neurons in the brain work. Each one of the dots in this image is a neuron, and they're all connected together layer by layer, from the input of what we see to the output of what we understand. And then what we do is we go through lots and lots of examples of cat and dog images. They're all labeled with the correct category, and we try to make a prediction. Initially, all of those neurons are just randomly initialized, so it's a complete guess. What we do is we calculate how far we are from the guess to the correct answer, the error, and then we use that error to adjust the strength of the connections between the neurons. And basically, we want to slowly move towards the right answer. After we repeat that, a million or so times, let's say, then what you end up with is a nice cat and dog prediction model. But what you actually want to do is, build a cat and dog prediction website, right? A user gives you a photo, and you have to tell them whether there's a cat or a dog in it. And the connection strengths that you learned during training are what allows your model now to generalize. So if you give it this photo, even though it's never seen it before and there's no label attached to it, it can get a dog prediction out based on what the model has learned via those weights attached to the neurons about the nature of cats versus dogs, at least in terms of the images that it's seen. But how much it can actually learn is a function of the model size and the complexity. And we just didn't have computer power and the tools to experiment with really big and complicated models until very recently. This picture is basically what neural networks used to look like maybe 5 or 10 years ago. And at that point, they had a small number of neurons. They were just fully connected between the layers. There weren't that many layers. And the end result was they weren't super powerful. In fact, for a problem like computer vision, they were almost written off compared to a specialized hand-tuned model that was built by experts for that exact task. Now you can compare that to a neural network model that we use today for image classification. This is called inception. And the idea is that you feed it an image and you get a prediction of what's in the image among thousands of categories. I think it's like 17,000 potential classes. And with a framework like TensorFlow, you can train a model like this that has tons of layers and is much more complicated than the early networks. That's what we mean when we say deep learning. The deep, in this case, refers to a deeper arrangement of layers and the more complicated connections that comes with that. The end result is that you have millions or even billions of neurons in your model. And that's what allows a deep neural network to get results that can actually vastly outperform the earlier hand-built, hand-tuned models.
So think about all of the science that you learned there, and when you go to your next cocktail party, how you'll be able to fascinate people with... No, seriously, the whole point of showing that is to demonstrate that for a long time, Google's team, particularly in search, used hand-coded algorithms. Some of those still exist, but now the data becomes much greater. It's beyond the human comprehension, so the machines learn to program the machines. In the future, everybody gets to choose their own digital assistant. This is mine. I chose it. I use this term predictive concierge-style search. There is something that's really important about this device that you're carrying around. Everybody assumes that if you pick it up and speak, you're asking Google something or you're doing some kind of search. Actually, about 60% of the time what you're doing is using an app. It's not always going to the World Wide Web. There is a difference between the internet and the World Wide Web. And when you're using an app, you're not actually going there. And your digital assistant begins to learn your habits and begins to learn what you want. So for instance, I always use this. The two things that I hate most in life, one is my own company, and second is my own cooking. So staying around at home is not a great idea for me. So I use OpenTable a lot. So if I use Siri to book a table for me and my friends, I don't want Siri to go and search for something at Google. I want Siri just to go to OpenTable, book the restaurant, and I want to get my points. So there is a big difference between search and service. And they're both connected in terms of the way that any brand who wants to connect with a consumer will have to be able to do both things. So the next stage in all of this is These kind of assistants are a bit flat. What if they had sentiment? What if they could understand humor? So this is a very short one just to show you how close we are to getting a digital assistant with a personality.
How many of you have seen this movie? In this movie, this is a robot that's assistant to the astronauts and the scientists. But this robot is also very empathetic. It understands emotions. It even has a sense of humor. And this is not that far in the future, even though interstellar travel is very, very far in the future. A machine like this is what we are building right now. So how are we doing? How do we do that? First of all, again, we use a neural network architecture called convolutional neural net to recognize human emotion from tone of voice. And the advantage of using CNN is that it will automatically extract features from raw input data, meaning you can speak to the machine directly without going through any signal processing and feature extraction, and the CNN will extract and recognize your emotion directly. That enables emotion recognition from tone of voice to be real-time and instantaneous, which is very, very important for human-machine interactions. We also have built a system in my lab which uses long short-term memory and actually reinforcement learning to learn to have a sense of humor. So we feed a lot of TV sitcoms, such as Big Bang Theory, such as Seinfeld, to this system, and it learns to do two things. One, it learns to recognize your joke. When you're talking, your humor, it learns to recognize that, so it will laugh or not, according to the sense of humor in your speech. And the second task, which is more elusive and much harder, is that the machine will come back with a punchline during the conversation with you when you say something. So conversational humor consists of a setup. You usually set up a scenario through conversation, and then there's a trigger for a joke, and then there's a punchline. And after the punchline, that's when people laugh. So this machine is learning to have a sense of humor.
That's when they're supposed to laugh. I'm going to
conversations.
actually try and skip this just a little quick move forward, because that's just a quick indication she starts to get a bit technical there about how they're actually doing it. What I wanted to do is show this final video, because this is what we've been talking about. Machine learning is at the future of marketing. Is your job actually going to be taken away by a digital assistant? So this final video is really interesting. It's not search related, it's actually social media, but it is an indication of where technology is taking over. So it was a demonstration live in New York last year where a young lady had to build a social media ad, put the campaign behind it, and this is how she did it.
Okay, here's the commuter bike event journey map. It looks like work's underway in a number of areas, and I've been asked to work on the paid social ad. I'll need to create an audience and assemble the actual ad and put it into market. I could use some help. Hi, Watson.
Hi, Melanie.
Watson, I'd like to target a new audience for the paid social ad interaction.
Okay, how can I help?
I'd like to start my existing buyers are for a similar category. Watson, show me how many customers have purchased from the road bicycles category in the last 3 years.
18,681 customers have made a purchase. Here are the details.
Okay, that's a good start. Watson, consider customer, social media, and third-party data, and suggest relevant attributes for targeting.
Okay, here are the top 6 attributes by frequency, with relevance score indicated by line thickness. Data sources indicated by color.
Watson, how many total customers have at least one of these attributes?
61,813 total customers have at least one of these attributes.
Watson, name this audience commuter bike event and save it with the list of attributes to the paid social ad interaction.
Okay, the audience has been saved.
Now let's use our partner's lookalike modeling to expand our audience. Watson, initiate a lookalike audience in our social channels using the commuter bike event audience and set the initial reach to 2 million.
Okay, the lookalike audience is being created.
Now let's use our customer attributes and Watson's understanding of this channel to refine our lookalike. Watson, which of these customer attributes can we use to better target our lookalike audience?
I have some suggestions.
Well, cool. I've got Watson's recommendations along with his reasoning for each. It looks like a couple of these would be a little restrictive, but the others correlate highly against a broader audience, so let's go with this. Watson, add the selected attributes as filters on our lookalike audience.
Okay, the lookalike audience has been created. Here are the details.
Okay, now we've got our audience defined. Let's go ahead and build our ad. Use the attributes from Commuter Bike Event and suggest images, text, and offers for use in the ad.
Okay, I'd like to better understand what these attributes mean. Do they relate to any of the following concepts?
Sure, it relates to health and commuter and zero emissions.
Okay, here are some highly relevant content options from eligible digital assets.
Okay, here's my image and my offer and my text. That looks pretty good. Watson, save this content into our paid social ad.
This content has been saved.
You know, I like what we have so far, but I think we need some options for people who want to commute in less than perfect weather because we want them to commute as well. Watson, suggest products relevant to cold or rainy weather.
Okay, here's what I found.
Watson, preview U.S. locations with cold or rainy weather during this event.
I've identified 4,863 locations with below average temperature or greater than 50% chance of precipitation during the event.
Enable dynamic content for locations experiencing cold or rainy weather during the event.
Would you like bad weather content to be displayed in place of other assembled content for these locations?
Yes.
Okay, I've created a dynamic content rule to display bad weather content for locations with cold or rainy weather.
Great. I'll notify the team we've completed our task and we're ready for launch. So I've had my paid social ad in the market now for a couple of weeks, and Watson's detected a couple of potential anomalies. But I'd like to take a look at what's going on here in this ad image. It looks like one of our images just it's not performing as well as expected. We've got a lower click-through rate than the other images. And Watson is recommending these other images, but why? Watson, tell me about the recommendation for this alert.
I recommend the following images based on the performance of similar images for this category in other channels. These images relate to the concepts humor, bicycle, and commute.
Watson, replace the non-performing image with the selected ones. Test and use the best performing image.
Okay, the image has been replaced. I will test these images for 7 days and notify you when the winner is chosen.
Thank you for your help, Watson.
I think her assistant is called Watson. Anyway, I think you get an idea of that. I hope some of these videos have been very helpful to get everybody on the same page. One last thing that I want to give you to take away. This is all about marketing in the age of assistants and assistants. I mentioned earlier on about keywords. Some of them are important, some of them are not so, in terms of being able to start helping and stop selling, which is a really great place to create that early brand affinity. There's a little tool here that I discovered. I don't know how many of you are subscribed to Think with Google. How many people? Take a look at the URL at the top. If you go over there and take a look at this little tool that they've put there. If you're involved in any of these areas of business, auto, beauty, finance, pet care, and whatever the other one is that I can't read. If you go there now, first person to get there gets dibs on it, and click on those icons, you'll get a word cloud of the most popular questions that people are asking. If you can create the content to answer those questions, then they become your customers. And that's it from me, guys. Hope you enjoyed it. Join me again for the keynote panel later on this afternoon.